we're working on solving the system of first order differential equations, right? Do you agree with me on that? Yes? So the story is this. We completed the solving the first order initial value problems, and then thank you. Okay, the story is this. We wanted to solve the higher order differential equation. Then we said, okay, we want to fall back on what we already know. So we made the change in variables. And once we made the change in variables, it transformed into a system of first order differential equations. And it was a difficult problem, so we wanted to solve an easier problem. And the easier problem was solvable using variable separable. And we solved it, and when we solved it, we saw that it pretty much led us to eigenvalues and eigenvectors. So we said, okay, whenever we have a system, we can use the help of eigenvalues and their corresponding eigenvectors to find the general solution. That's the broader, bigger picture, right? So then we said, okay, if you have a system x prime equals ax, we said the first step would be to find the critical point. Okay, it's not there. Maybe I should include it. To find the critical point, step 1 is to find eigenvalues, step 2 is to find the eigenvectors, step 3 is to find the general solution, right? And after that, sketch the phase portrait and classify the critical point. And now remember, when we find the eigenvectors, I demonstrated for you that each of the eigenvector is in fact the solution of the first order system. Do you remember that? Yes? And the eigenvectors are linearly independent, so they form the fundamental set for the first order system of equations. Okay, that was what we were working on. And then we said, okay, I said that there are 9 different cases. You could have real and different eigenvalues, both being positive, both being negative, one positive, one negative, 0, and the other one being non-zero. You could have real and equal eigenvalues, one of them both being positive, both being negative. You could have complex eigenvalues where the real part is positive, real part is negative, or the real part is 0, which means a purely imaginary complex eigenvalues. These are the how many cases? 9 cases that you will run into. Okay. Now, the one problem that we picked up was, we said the sample solution curves would look like that when the eigenvalues are real and different. Okay. Then we wanted to solve a problem like this, and I demonstrated how the critical point here is 0, 0. And I found the eigenvalues. Eigenvalues turned out to be -1 and -2, right? Real, different, and negative eigenvalues. Then I found the corresponding eigenvectors. One of them turned out to be 2, 3. The other one turned out to be 1, 1. Okay. And then I wrote the general solution here, and I said, okay, the general solution is that. And because your eigenvalues are real, different, and negative, you can just classify the critical point as asymptotically stable. And I think, and the other one I did was, okay, because my eigenvalues are real, different, and negative, as t goes to infinity, my solutions are going to 0, 0, 0, 0, and as t goes to negative infinity, the solutions becomes infinite. That is where I am, and I sketched my eigenvalues, and I sketched that at different points. I'm experiencing force in these directions. Is this clear? This is where we stopped. So all that I need to do today is to sketch the solution curves, and you should be all set. Clear? Are we all together on this so far? Any questions on this problem so far? No. Okay. So what we were doing was this is my solution. So let's look at I don't know why I'm not. Okay. Just give me a moment. I don't know what's going on, so I can't tell you why it's not working.